So as I was saying, in this talk, I will present some part of my PhD research about computing geodesics on the Stiefel manifold, calculating the distance on this manifold. So the motivation is given by the fact that there are many applications in diverse fields, as we will see already in this talk and also in the upcoming talk. Like in optimization, let's say probably the original interest was in optimization, then image and signal processing, statistics, and many other fields. So let's recall this: the Stiefel manifold is just the set of orthonormal matrices, which means matrices whose columns are orthonormal. Usually we use N and P for its size. And then we can see that, so there is some theory behind that attaches to this set a manifold structure. So it can be proven that it has a structure of a smooth manifold. Some of these applications, they deal with the evaluation of the distance. They need the evaluation of the distance between 2 points on the Stiefel manifold. And for this distance, there is no closed form formula available. So that's the reason for considering numerical algorithms, numerical alternatives. So in this talk, I will start with some motivating example. So let's say for the general case, there is no closed form, but if n is equal p, we have it coincides with the orthogonal group. And in this case, there is closed form solution. And also if p is equal 1, it reduces to the unit hypersphere in Rn. Yeah. So also in that case, so in the special cases, there is, of course, there are explicit formulas available, but not for the general case. So usually we are interested, this is also a good point. So usually we are interested in the cases in which, so P is different from N and P is different from 1. And usually P is much smaller than N. Usually in the application, this is the case, but maybe there are also other applications, but yeah, let's say usually P is much smaller than N. So I will start with a motivating example. It will, let's say, just be a kind of illustration to see what geodesics can look like on this manifold, and also maybe on general manifolds. Then we'll go to some more mathematical part about the geometry of this manifold. I will discuss the computational framework based on the shooting method, which is a classical numerical algorithm for solving boundary value problems. And then we'll see some example applications like what I mentioned at the beginning. And this will, let's say, recall also the first motivating example. So it's at the same time motivating example and a running example, let's say. Yeah, so let's start with this example. So sometimes in imaging, the need arises to deal with transformations that are more complicating than just similarity transformations like translation, global scaling, or rotation, of course. So for example, that's the case if the plane containing the shape you are interested into is not parallel to the plane of the camera. So this creates a kind of distortion, right? Creates distortion, or other cases in which there is like a perspective, a change in perspective. For example, if we are imaging the same scene from two different point of view, from two different angles. So here you have the example. Here you have two shapes from the MPEG-7 dataset. It is a quite well-known data set that contains many different shapes, basically in sets of 20 similar images. Like each set, for example, this set is called device 7, I think, or some device, and it has 20 shapes that have some kind, yeah, you can see just by looking at them that they have some kind of similarity between them, right? Because, like, for example, if you look at these two shapes, they both have six spikes. They are both like inscribed in a kind of circle, so there is some kind of circular pattern. Yeah, so it might be a natural question to ask how far are they from each other. So if we can attach a structure to these shapes, a mathematical structure, then we can measure how far are they from each other in a certain sense. Okay. Yeah. So one usually needs to go beyond the similarity transformations that I just mentioned. So global scaling, rotation, translation, to define shape equivalencies or to compare them to see how far are they from each other. And here you have, so it's just an illustration of what geodesics may look like on the Stiefel manifold of dimension n times 2. Okay, 2, it's because they are two-dimensional. So they are in a Cartesian plane, flat plane. Okay, so two-dimensional plane, as you can see, and the n is just the number of points. So now, okay, you cannot see this because the points are they merge kind of each other, so they look a bit like continuous lines, but yeah, they're actually points like in the previous slide. Okay, yeah. So n is just the number of points, and the reason why it's not fixed is that maybe the number of points of this one, it's not the same of this one. Okay, but for each row, it is the same n. Okay, so that's why I didn't write it. So it's just an illustration. So these two shapes are the same that I showed in the previous slides. There are some technicalities behind. Maybe I can explain later at the end of the talk. So of course there is some kind of pre-processing, but I'm not going to talk about that. So, but it's basically just consisting of some projections. Okay. But okay, let's just say it's not rigorous, but let's just say that they look like this, the geodesics on these manifolds, and I consider these two shapes, the light blue ones, as endpoints, and then I constructed the geodesic connecting these two endpoints, and then I just decided, okay, this is just my choice. To consider 8 points on this geodesic, equally spaced, and these are the 8 points. So each point is represented by a shape. Okay, so you see that. Okay, this is, let's say, the shortest path. Yeah, so I will talk about geodesic, let's say, from a mathematical point of view in the following slides. But let's say it's the shortest path on this manifold between these two shapes. Okay, and that's just a way to see what they might look like. Yeah.
So here you just put, say, the coordinate of each vertex.
Exactly. Yeah. So
in a metric, then is also you, but and then you consider it as a point in the Stiefel manifold.
Yeah. Yeah. Exactly. Yeah. Okay. So each point is an orthonormal matrix of size n times 2. Yeah. It's just that. The 2 is because it's bidimensional. It's on the Cartesian plane. It's not. Yeah, exactly. So yeah, exactly. Yeah, that's why I said. Yeah. So there is a projection. Then you are on Stiefel manifold, and then I mapped them back to the original space. Okay. So this, let's say, kind of technicality I wanted to hide, but yeah, it's just. Yeah, because otherwise it will take too much time to explain everything. But of course, I mean, we can discuss everything. Yeah. So you see, this. So then you can compute the distance between the shapes. So they are on the same geodesics. We can compute the distance between this shape and that shape. And okay, you can see the values on the right column. But okay, this is just to give, like, to see something at the beginning. and we are going to see the math in the following slides. So yeah, so let's see the geometry of this manifold. So as I said, is the set of matrices with orthonormal columns, matrices of sign. Yeah.
If you do some computation of all your figure, would we see the
of the original? Sorry.
If you do some rotation, right? The point are different.
Yeah.
If you project to the Stiefel mirror, can it recognize the same one?
No, because
right?
this. Yeah. So the problem you're referring to would have to be considered on the Grassmann manifold. So basically, it's a quotient. Yeah. So we should quotient the. Well, actually, so I think so. For the Grassmann manifold, there is a closed form formula for the distance. It's basically so it's the principal angles. It's like principal angles between subspaces. Yeah. So let's say from that point of view, it's easier because there is the closed form formula. So it doesn't give rise to all the numerical discussion that I'm going to do here. Yeah. Yeah. So, okay, for the purpose of the talk, and also as you have already seen before, and for the next ones, since we are considering an embedded submanifold, often I represent it like a two-dimensional surface embedded in three-dimensional space. In general, it doesn't look like that, but I mean, it's a good way to think about it. Okay, so because I think everybody understands what is a surface, what is the tangent space at a point, the geodesic on it, a curve on the surface, etc. So yeah, the first object we introduce is the tangent space to the manifold at a point x. So it is the set of all tangent vectors to the manifold at x, with this notation. For the Stiefel manifold, the explicit expression is this one. Okay, and for the calculation, what is more useful is this alternative characterization of the tangent space, because it gives, let's say, an explicit format for the tangent vectors. So x is just the point, is a point of the Stiefel manifold. Okay, it is an orthonormal matrix. X perp, it is another orthonormal matrix. It is of size n minus p times p, such that the subspace spanned by X perp, it is the orthogonal complement to the subspace spanned by X. In this way, if you put them together, X and X perp, they form an orthonormal basis for the entire space, for the embedding space. Yeah, the embedding Euclidean space. Okay, so the format is this. So you have X times omega, which is an is a skew-symmetric matrix. Yeah, this definition of size P, plus X perp times K. And on K, there is no special, it has no special structure apart from its size. Yeah, it is n minus p times p. Okay. Yeah, so this is an explicit format for the tangent vectors on the Stiefel manifold. And also from this format, it's really easy to calculate the dimension of the Stiefel manifold, because since the dimension of the Stiefel manifold, so the dimension of a manifold is equal to the dimension of the tangent space. Yeah, tangent space to a point, to the manifold. We can just count the dimension. So the dimension of the skew-symmetric, of the space of the skew-symmetric matrices, which is denoted by SQ. Okay, but it's the dimension of this space and the dimension of the space of the matrices K. Yeah. So the space of skew-symmetric matrices of size P is 1/2 P times P minus 1. And this, of course, is n minus P times P. And then you do the sum and you get this result. So it shows that even if the matrices are of size n times p, the total number of degrees of freedom is not n times p, it is less. Yeah, it makes sense, no? Because we have some constraint, right? The orthonormality constraint, and this can be seen behind also from this structure. Okay. Yeah. Okay, then so far we haven't talked about inner products. So if we want, yeah, you have a question? It's okay. If we want to compute distances, we need to introduce inner products. So in the context of Riemannian manifolds, it's called metric. So yeah, so okay, let's just remind that a manifold, a Riemannian manifold is a manifold endowed with a smoothly varying inner product, which is called Riemannian metric. Okay. So rigorously is a couple, so there is a manifold and a Riemannian a Riemannian metric on it. So for the Stiefel manifold, there are two popular options. So the first one is just to take the embedded metric inherited by the tangent space from the embedding space, the Euclidean space. So it's just this inner product. So psi and eta are two tangent vectors at 2m at x. Okay, and yeah, so there are two matrices, and we just take the trace. So this is the trace operator of x transpose eta. Yeah, this is also sometimes called this is a Euclidean. Yeah, it's a Euclidean inner product for matrices. Okay, sometimes it's called Frobenius inner product because it induces a norm which is called Frobenius norm, which is just a Euclidean norm for matrices, let's say. And the other option is called canonical. The other option for metric is called canonical metric, and this is given by seeing the Stiefel manifold as a quotient of the orthogonal group. Yeah, and this is the metric that I usually considered in all the following slides, and so in my work, it's usually this metric that I considered. And in the next slide, I explain why. For the moment, just point out that the only difference with respect to the Euclidean, to the Euclidean metric, is the presence of this factor in the middle. So you see, it's a kind of projector, but not really, because there is a factor 1/2. So, yeah. But okay. So metrics, so inner products that can induce a norm, and the two norms we can compare here for, let's say, consider a given tangent vector psi in that format that I showed before. So the format of tangent vectors to the Stiefel manifold. And if we compute the Frobenius norm, so the Euclidean norm of this vector, which is just a matrix, this you do the calculations, and this just gives. So this just basically is the definition. So it gives the square root of the Frobenius norm of the skew-symmetric part squared plus the other matrix K, which has no special structure, its norm squared. And if you do the same thing with the canonical norm, you do the calculations, and you see in the end, the only difference between the two is this factor 1/2 that appears here, this 1/2. Yeah, now, okay, I wanted to do that, but then I forgot. I wanted to write an example of a skew-symmetric matrix. If you think of a skew-symmetric matrix, the upper triangular part, so it's a definition like upper triangular part, the coefficients in the upper triangular part are minus the coefficients in the lower triangular part. So in reality, so let's say if it is a P by P matrix, the number of degrees of freedom is the one that I said before. So the dimension of this space is 1/2 p times p minus 1. Yeah. So when you do the Euclidean norm, if you think of this part, basically you are so you have twice the square of the same coefficient. Yeah, just think a moment. Sorry, I forgot to write this down, but I can write it down later. So yeah, you have twice the square of these coefficients. Yeah. So you put here, there is 1/2. So they are considered only once, as let's say it's more natural, let's say, because this takes into account the fact that the true degrees of freedom of this manifold, well, so they are less than n times p. Okay. Yeah. For both these metrics, the Euclidean and the embedded and the canonical, there are closed form solutions for a geodesic z of t that realizes a tangent vector psi at a point x. So we have the closed form solution of z of t, the geodesic. So here I reported just the closed form solution for the canonical metric. So if you change the metric, the expression of the geodesic changes. Okay, so maybe now you might be wondering, okay, but if we have a closed form solution, yeah, well, why you consider numerical methods? Well, because it's a different kind of problem. So this gives the geodesic once you have x and psi, you have, and then gives you z of t. But the problem we consider in the following is, given x and y, we want to find the distance between them. It's a kind of inverse problem. It is the inverse problem, actually. Yeah, so for this problem, there is no explicit formula available in the general cases of the Stiefel manifold. Okay. Yeah. Okay, so, and okay, to tackle this problem, we introduce other important tools from Riemannian geometry, the Riemannian exponential and logarithm mapping. So given a point, and here I illustrate them for the special case of a unit sphere, which is also a special case of the Stiefel manifold. So yeah, so I think it's a good concrete example to focus our ideas on. So given a point, so you can look at the illustration. So given a point x on the manifold and a tangent vector in the tangent space at that point, the exponential mapping exp at x is a mapping that goes from the tangent space to the manifold, such that it maps this tangent vector psi is defined as gamma 1, with gamma being the geodesic that is emanating from this point in that direction of psi. Okay, so it is this point. Then, of course, well, this is kind of natural. There is correlate. It tells you that, okay, if you scale the psi inside, then you just have a point on the geodesic which is parametrized according to t. Okay, yeah. So if you scale psi, you will move along the geodesic. And then we have the inverse. The inverse problem is called logarithm. Inverse mapping is called logarithm mapping. So if we for any two points on the manifold, like they are in the sphere, the inverse mapping is denoted by x inverse of y, or also with log. So it's called the logarithm mapping. Okay, so given x and y, it gives us psi. Yeah. So for the sphere, there are, as I mentioned already before, so there is also the closed form solution for the logarithm mapping. Okay, you just don't need to look at explicit expression, but just for telling you there is. Yeah, and it's a special case of the Stiefel manifold. So in this case, there is the explicit solution. Yeah, and this is a general property. So given 2 points, but here I state is a general property, but here I state it for the Stiefel manifold. So given 2 points, x and y, such that the exp of psi, a tangent vector at x, is equal to y, the Riemannian distance between these 2 points equals the length of the tangent vector psi, okay, which is what is written here for the canonical norm. Okay, so this is important because it tells us, okay, if we want to compute the distance between 2 points, so it gives us the recipe, let's say. So we have to find the tangent vector, which is equal to the logarithm mapping of y at x. So first we compute the logarithm mapping, and then we compute the norm of this tangent vector. Okay. Yeah, so which is what I state here. So it is equivalent to compute the length of the Riemannian logarithm of y with base point x. So first compute the logarithm, we get psi, and then compute its norm, and this gives us the distance between the 2 points. So this is the idea. And the problem, as I had mentioned before, is that there is no closed form solution for the Stiefel manifold, and that's where, let's say, numerical methods enters in. So far I didn't talk about numerics, so now we are going to see some numerics. Do you have any questions so far? Yes?
So for the log map, I don't think it's defined for any xy. So why should that be the total constraint?
Yeah, exactly. So usually we so for existence and also uniqueness, we have this only in, well, mostly for uniqueness. Sorry, locally it is unique. This so locally we have a diffeomorphism between the tangent space and the manifold, but globally it's not unique. Yeah, but
You say there's no closed form solution. Is it because there's no closed form for the exponential map or the logarithm map?
so the closed form solution for there is no closed form solution for the logarithm mapping, because for the exponential it is the one given by the geodesic here. Because if we put t equal to 1, it is exactly the definition of the Riemannian exponential. Yeah, but it's the other mapping, so it's the inverse mapping that we do not have. Okay, thanks. Okay, so continue to the numerical part. So I will talk about the shooting method, which, as I said, is a classical numerical method for solving boundary value problems. And before applying it to the Stiefel manifold, I will show just let's say the original Euclidean version for ODEs in the flat space. Yeah. So a boundary value problem is a problem that has this kind of form. For example, for a second order ordinary differential equations, we want to find Wx, the solution that on an interval to R that satisfies this ODE plus the boundary conditions that at the boundary of the interval we have some prescribed values alpha and beta, which are just some real scalars. Okay. Yeah. So classically, what is done is to recast this problem into an initial value problem. So we want to find Wx that satisfies. So the first part here is the same. So it's always the same ODE. But now we don't have boundary conditions, but we have initial conditions. The first initial condition, it is exactly the one that we have here. So it's the same. But okay, initial condition because it is the beginning of the interval. Okay, it's the left-hand side. But then now the other condition is a condition on the first derivative of the solution, which is imposed, always at the beginning of the interval, so that's why they are called initial conditions, equal to a scalar S. And yeah, so the idea is to find this scalar S, which you can see as the slope. Well, it is the slope of W at the beginning of the interval. Find the scalar S such that we can enforce the second boundary condition here, because that is our original problem. We want to solve the boundary value problem, but we go through this because for this we have theory and numerical algorithms. So this problem, the initial value problem, in general has a unique solution which depends on this parameter S. Okay, you have a classical theorem that tells you this under some mild conditions you have unique solution, existence and uniqueness of the solution, and this solution can be found either, so you can have either analytical solution, such as it is the case for the Stiefel manifold. So the equation of the geodesics is a solution to a boundary value is a solution to an initial value problem. Or numerical solution, and then you can resort to some numerical, classical, or also more recent numerical methods to solve this kind of problem. So some of the most classicals are Runge-Kutta methods. Classical and powerful methods for solving this kind of problems. But this, anticipation, this we will not need, because we have the analytical solution, so the one for the geodesic. So this Runge-Kutta is just for problems that do not have the analytical solution. So, given this problem setting, the single shooting method for boundary value problems reads like this. So we define a function which basically is, let's say, the mismatch, the discrepancy, if you want, the difference between the solution W that we find by solving this problem with the parameter S at the right-hand side of the interval at B. This is exactly, so it is this one, right? And there we want to enforce that the value of W at the right-hand side of the interval has to be equal to beta. But it will not, we just choose some value of S, it will not be in general. So we consider their difference, the mismatch, let's say. And we define this function, a nonlinear function. And now what we want to do is to find S bar such that f of S bar is equal to 0. So basically it boils down to a root finding problem. So you can use any classical root finding method to find the S bar such that this is equal to 0. Because then when this is equal to 0, you have enforced the second boundary condition, which is our problem. Yeah, usually this is done with Newton's method, but one can in general use any other fixed, Newton methods is also a fixed point method. So fixed point iteration method. You can use any other method. Yeah, you have questions? So this is, let's say, the version for, so it's not yet applied to the Stiefel manifold. So I want to show you how it looks like, some iterations of this method for a given problem. So as I said, we have an interval AB. We have some values at the boundary of the interval, alpha and beta, just two scalars, two reals. And we want to find the solution, so the W that satisfies the boundary condition. So the first point is already satisfied because because of the way we define the problem, and we want that this point coincides with the beta there. So at the first iteration, you just choose a first value, an initial guess of S, so that parameter that we want to find. We want to find the S bar. Just choose S0, and then according to, so which is the slope of W at this point, A alpha, and which is denoted by this arrow here. And then you, let's say, and then you calculate the solution, you shoot, yeah, like it really looks like shooting in that direction, hence the name of the method. And you shoot, you find the solution, and you arrive at this point at the right hand side of the interval. But it's not what you want, because what you want is to arrive here. So there is this mismatch. So this quantity is exactly this mismatch is exactly what we define here as this difference, right? Yeah. So what we want to do is that this mismatch goes to 0. And so based on this mismatch, you construct your iteration, and you want to reduce this. So at the following iterate, you come up with a value of S1, which is hopefully gives you a better solution. And this, yeah, so what happens is, like for example, in this case, which I did with MATLAB, S1, you start from here, you should find the solution, and it arrives here. So it's not yet the good, there is still a mismatch. And then it continues like this. So, and then it iterates, yeah. And then it iterates. So at the third iteration is already very close. I can see like to the value, to the boundary condition that we want to enforce. And then this is the fourth, the third iteration. No, wait. Okay, so this is just initial guess, first iteration, second, third. You don't see any difference anymore. Well, at least visually. Then of course there is a tolerance, and you're like a small tolerance that, yeah, gives you.
Is there like a smart way to adjust the slope? Because the shooting method is about the slope, right? So when you first.
Yeah, you mean for the initial guess?
Yeah.
Yeah, there are. This is, let's say, this is almost, because what we know is there is so if we use Newton's method, so we know about its local convergence, but we cannot say anything about global convergence. So let's say if we start close enough with some reasonable value, and there are some techniques to choose the initial guess, then we know that it will converge to the solution. Yeah. But yeah, so there are some methods to choose some rule of thumb. So let's say to choose S0. Yeah. And then, if it started so correctly, then let's say sufficiently good, then it converges, and it converges quadratically. That's why you see that, like in 4 iterations, you don't see any difference anymore between, at the end of the interval. Yeah, and this is another slide, but it looks the same. Okay, so given that method, we want to apply to that problem on the Stiefel manifold, and formally it looks exactly the same, because we have a second order ODE. I didn't for the geodesic, but of this ODE we already know the solution, the explicit solution, which is this one. Okay, so that's why I said we do not have to use like numerical methods like Runge-Kutta or Euler method, etc., to solve this ODE. In this case, luckily, let's say, we don't need it. So we can just use this one with boundary conditions, define the function that gives let's say, the mismatch, okay? Because when we shoot with x and a certain psi, we find the y. We find the z at t equal to 1 psi, which is just the exponential, okay, the Riemannian exponential. But we want to arrive at the point y, okay? And this will not be the case for, let's say, the initial guess of psi. So, okay, here psi plays the role of the parameter S in the slides that I just showed before, okay? Because this is the value that we want to find. This is let's say, yeah, the root we want to find. This is the variable here. We want to find the psi such that this nonlinear, such that it is a root of this nonlinear equation. Okay, formally it looks exactly like the other problem, but before S it's real, here it is a matrix. This psi. Okay. Yeah, and okay, and we do this with the Newton's method. Yeah. So this shooting method you can find in this paper of Breiner, which is also the author that considers those shapes that I showed at the beginning, which was also on the website of Meta. And my PhD thesis and another preprint. This is the method we use to find the distances between points on the Stiefel manifold. Yeah, and I just want to show you how it looks like its convergence behavior. So this is a very simple numerical experiment on the Stiefel manifold 15(4). There is no particular reason why I chose this parameter. I mean, it's just to have an example and to show that the monitored quantity, which is the norm of the residual of that nonlinear equation, goes to 0, and it goes to 0 quadratically. So here you see a plateau, a stagnation, because we have reached the machine precision. So the default one in MATLAB is double precision, so it's around 10 to the minus 16. Yeah. So okay, it's yeah. I mean, so it's a very fast method because you have in 5 iterations it has converged to full machine precision. So this is a very desirable property. A drawback is, as also Maupay said, so we need a good initial guess to start the method. So yeah, so let's say then if the problem is local, so if the 2 points are close enough in a certain sense, then this problem can be solved very well by single shooting. Otherwise, one could use some kind of, let's say, globalization techniques, like introducing some conditions, like for using, because okay, here I always use a unitary step size for this method. So when I find this psi, I just use the full psi and I do not scale it, let's say. But one could introduce a parameter to scale it, so like a step size, a non-unitary step size, so you can use some kind of Armijo condition or Goldstein condition that are usually used in optimization methods, like in steepest descent, to make the shooting more robust. Yeah. Okay, so the last 10 minutes, let's see some applications. They are not difficult applications, so that's more for illustration purposes. Well, okay, it looks complicated, but so it's just an example. It's just an example. I'm not a specialist of model order reduction, so that is the field from which this application comes from. I'm not a specialist, but the reason why I consider this problem is that I saw that there are some orthonormal matrices popping up. So they are points on the Stiefel manifold. Yeah. So model order reduction are techniques used for dynamical systems parameterized according to some parameter. And so for each parameter in a set of parameters, one uses a proper orthogonal decomposition. So this is a name that comes from physics, I think, but basically it is a variant of the SVD. Okay, so if you know the singular value decomposition, you have never heard about this, is fine, because It's basically just another name. So one used this POD, this proper orthogonal decomposition, to derive a reduced, what is called a reduced order basis, which is just a matrix that which is orthonormal, so it belongs to the Stiefel manifold, and it has dimension, it has size n times r, and usually, and r, it's not usually, it's what you want. Now I will explain why. R is much less than n. Okay, so the reason is, so this is a dynamical system. Okay, you don't need to understand everything, but okay, I mean, it's just, this is just an ODE with some matrices A, B, this another, yeah, these are coupled through X and another matrix. So usually these are big matrices. You have big matrices A, B, and C of size n times n, n times m, etc. And what you want to do is to reduce what they do in this field. They want to find a smaller dynamical system, this one, where R is much less than N, which is the size, let's say the characteristic size of the original dynamical system. So that's also the reason why before, at the beginning of the talk, I said usually, so the Stiefel manifold, you have like N is very, I mean, N is very big and P is very small compared to N. So this is an instance of what I said before. Here the P, what I called P so far, is called R. Okay, that's the reason, because it stands for reduced, so reduced order system. And so these reduced quantities, vectors and matrices, are just given by projections. Okay, so these are kind of projections when we do V transpose times the original vector, V transpose, and this is sandwiched. So V transpose AV, so it gives a matrix AR, which is of size R times R. Okay, so a smaller matrix, etc. So that's why I highlighted them in yellow. So they're all reduced matrices and vectors. Okay, and this they do for several, since this system is parameterized according to P, they do for several values of P. So for each value of P, one gets an orthonormal matrix. And so if we have capital K values of P, we have K orthonormal matrices. So all these matrices are orthonormal, so they are like points on the Stiefel manifold. Okay, this is the setting. Okay, so that's the point at which the Stiefel manifold enters in. So now what's the problem that they consider in this field? So now let's say that you are a new parameter value P hat. So we can obtain a new orthonormal, an orthonormal basis V hat corresponding to P hat by interpolating the local basis that we already have. So this set here. So we already have this set here. Now we are given a new P hat. We want to obtain V hat starting from that set. So basically without performing the proper orthogonal decomposition again. Maybe because the system is really, really big and that is too expensive. And we already have these matrices V from V1 to Vk. We want to use them. Okay. So what they consider, so this has been around for quite some time, as you can see, 15 years at least. So the interpolation, what they consider is the interpolation in the tangent space to the Stiefel manifold. Yeah. So these are some references. It looks something like this. We have already seen something similar pictures like 2 months ago, but this is yeah. So the idea is we have these points, these orthonormal matrices on the manifold. Like here, I just considered 4. We choose one of them as an expansion point. This here in the illustration is V3, and we construct the tangent space. We consider the tangent space, and all the other V1, V2, V4, we lift them to the tangent space at V3. And then when we are in the tangent space with these capital gamma vectors, it is a Euclidean space. So we know how to perform interpolation in Euclidean space. Then it can be it can be linear interpolation, quadratic interpolation, whatever you want. But in Euclidean space, we know how to do interpolation. So we do interpolation in Euclidean space. Let's say that we find a gamma hat. And once we have found the gamma hat, we project, we use the Riemannian exponential or another projection to find the new orthonormal basis on the Stiefel manifold. Okay, it's just it's just to give you an application in which because for doing interpolation you need the distance between the points, and that's where these algorithms for calculating the distance enter in. So for interpolation on the tangent space, the distance is needed, and so we need those algorithms. Okay, so here I had some numerical results about this, but maybe yes, running out of time, so let's skip this. The details are in my PhD thesis. If you want to have more details, let's see the Riemannian center of mass that we already mentioned a couple of months ago, but let's see it again. So the Riemannian center of mass is the notion of mean, is a possible notion of mean on a Riemannian manifold, and it is defined by the optimization problem. So it is the minimizer of the 1 over 2n, where n is the number of points of the sum of the squared Riemannian distances between the optimization variable and the points qi that we have. These are just a capital N points on the manifold. Okay, so we have n points on a manifold. We want to find their average, but not their Euclidean average. We want to take into account the curvature of the manifold. Okay, so the fact that it is a manifold. Okay, so this d is the Riemannian distance. So you already see that for if we consider Stiefel, we don't have the closed form formula, so we have to resort to the numerical methods to compute. So we can use our algorithm, for example. Okay, this is a more let's say this is a more theoretical warning, because on manifolds of positive curvature, the Riemannian center of mass is in general is not unique. The Stiefel manifold has also positive curvature, but okay, we have theoretical results that guarantees us that if the data points, so if the data points, the qi, are close enough to each other together, then uniqueness is guaranteed. So for these theoretical results, for example, you can see this paper, or this author did, Afsari, the first one, also have other papers about this.
Does one know how large is the set? Right? It's not even about the curve or
like the radius, you mean?
The center, like if you find a point minima, right?
Yeah.
It's not unique, so the locus.
Yeah, the locality, they have bounds estimates in their paper, and especially, and also another paper, an earlier paper by the author about this. Yes, but I don't remember the bounds, but yeah, there are results. But I mean, if the points are reasonably not something completely different from each other, like in the case of the sphere, like if you have antipodal points that are exactly antipodal, like north-south pole, yeah, that is like a pathological case, because you have an infinity of geodesics that connect these 2 points. But in practical, so these are nice, interesting theoretical aspects, of course, but for us, like in a numerical, in an applied setting, it will never happen. I mean, like in reality, it will never happen that we have 2 points that are like exactly antipodal, like on a sphere. You see what I mean? So yeah, that's why I said, okay, so you have to be careful, but in applications like pathological cases, probably will not arise. Yeah, so you also have more specific results, for example, about the curvature of the Stiefel manifold. So some authors gave upper bound on the curvature. So we know that it's positive, of course. We don't have an explicit formula, we have bounds. Yeah, so maybe just the last thing. Okay, so a Riemannian center of mass. Okay, so we go back to that example. I said at the beginning, in the MPEG-7 data set, we have many sets, many sets of shapes. Each set like contains 20 shapes that they have kind of similarity. Okay. So this is device 7. Yeah, I think before it was another one. Okay, so this is one set in this MPEG-7. Yeah, again, you can see they have all some kind of similarity. Okay, so this is just an illustration of what does it look like to compute the Riemannian center of mass. So the average of these points, considering that they can be represented on a manifold, and this is the result. And so this result I computed with that shooting method for the distance. Okay. Okay, so we are not doing shape analysis here. This is maybe this will be for next talk, which will be really on image segmentation. But let's say this is really just okay to give you an idea. So yeah, we have a very nice theory. It can also be a very abstract object, but at the same time we can also have something that we can visualize. Okay, so that's just to give this kind of idea. Yeah, so it's always the paper, okay, it has this application. Okay, and then there is something in summary statistic, but I think, okay, I will stop here, okay, and if we want to know more, okay, so let me just go to the last slide. So I will put the slides. Maybe I can also on the Meta website or on my website. There are already the slides of a previous talk that I gave, which is very similar, but here I added some mathematical details. So we have seen that computing a distance on a Riemannian manifold can be a hard problem if you don't have the explicit solution. I discussed this shooting method, and I presented applications in like imaging, so shapes and model order reduction. There are also these applications in summary statistics, which is nice, but at the same time, okay, I skipped for a reason, because it's a special case of the sphere, so we don't really need the Stiefel manifold. So okay, but it's still nice to look at it. We can discuss it later. And the outlook. So recently there have been many advances in the numerical algorithms for computing this distance. This is really new. They do. This author is studied Stiefel, the logarithm mapping, computing the logarithm mapping on the Stiefel manifold for quite a few years, Zimmermann, and they do a kind of review of all the techniques, considering both accuracy and performance. Okay, and then here you have some, let's say, novel applications that always deal with this distance. So I mean, there is motivation to compute this distance. Apparently, we will see. So we have already seen like the federated learning paper. They also consider the Stiefel manifold. They also said, okay, we need the distance, even if then they do some kind of approximation, but okay, it's always related to this. And we have many other papers now, also with medical application for electroencephalography data, brain network harmonics. Maybe we will see this next. But for the next talk, I will discuss an older paper, but it still remains important because it both discusses a couple of methods on Riemannian manifolds, which give superlinear convergence. So they are okay. So the fact that I discussed a bit the Newton methods, etc., quadratic convergence is also a bit related to this method, BFGS. So they have a faster convergence than steepest descent or gradient method, okay, in general. And its application to image segmentation on the Stiefel manifold. They also consider the Stiefel manifold in this paper. So yeah, so I will talk about this next time. Okay, thanks for listening.